Thank you everyone for joining us for your lunch hour. Welcome to Wireless Broadband 101 with NoaNet. We have Greg Berry and Sean Ogden, two of NoaNet's network engineers, with us today to discuss wireless technologies, their capabilities, their challenges, and potential use cases for them. If you have any questions for these guys, go ahead and drop them in the chat or the Q&A at the bottom of the screen, and I'll try to pose those to them live while we're on the topic. With that, I'm going to go ahead and turn it over to Greg to get us started. Thanks for doing this, you guys.
Thanks, Claire. Hi, everybody. My name is Greg Berry. I'm a senior network engineer with NoaNet. Been working with NoaNet for about 8 years. Mostly been working on the layer 3, layer 2 systems, deploying broadband systems around the state for various customers. For the last couple of years, we've been working a lot on deploying wireless systems. Mostly, I mean, since I started with NoaNet, we've actually been doing wireless, mostly microwave, but over the last couple of years, we've been deploying some private LTE systems for different customers. And just a little bit of history about me. I studied electrical engineering, worked up in Alaska doing working on wireless projects up there. Where up there, it was probably about 95% wireless systems and 5% fiber, and then came down here to Washington where the topography is different. So there's a lot more fiber here in Washington, and so just naturally most connected things up mostly with cable plant, fiber, copper, and of course using wireless to get to hard to reach spots that were probably too expensive to build to. So today we've got Sean Ogden here. He's our new wireless engineer. We've been working together closely over the last couple months, getting up to speed on what we've been doing with private LTE and our various microwave systems that we've deployed and that we are going to deploy. And we've got lots of different projects on our plate that we're going to be working on here. And just a little bit about NoaNet for those that don't know anything about NoaNet or just kind of, or maybe just a little refresher. NoaNet is a wholesale broadband provider. We've got fiber around the state. I hear 3,000 miles of fiber, both aerial and underground. Our customers are mostly other ISPs or government entities. We're made up of a consortium of public utility districts around the state, and you can see at the bottom right of the slide the different PDs. We also one of our members is Energy Northwest, which I don't think they're considered a PUD, but they're one of our members. We also worked with the state very closely on deploying the next generation 911 system, and that's a collection of 70 PSAPs scattered around the state, and we built a system, a highly reliable system that provides 2 paths into every PSAP, and then we bring that traffic back to a couple different data centers, and so that's just a little bit about what we've been doing. We over the last couple of years, we've been working a lot with customers, doing a lot more professional services, consulting, and helping customers deploy broadband systems, whether wireless or wired. And so today we're going to talk about mostly the wireless side of things and how that kind of fits in with the wired systems. So with that, I'm going to go ahead and pass it over to Sean, and he's got a slide deck here he's going to go over, and Sean comes to us from I'm sorry, I forgot the lab name in Idaho. With that, I'm just going to go over to pass it to Sean. He can give you a little bit more history about himself there. Thank you.
Sure, thanks, Greg. It was Idaho National Laboratory. I just came to Washington from that location. My name's Sean Ogden. Primary background is military communications. I was in the Air Force for 4 years, and then after that went and did 6 years as a contractor in Iraq and Afghanistan, supporting those efforts over there as a communicator. Came back and have worked in various roles in networking and wireless design since then. So today we're going to go over the basics of wireless and then get into wireless broadband specific type equipment. So with that, let's roll into it. The basics of wireless is that it's transmission of information using radio waves. If you look at the different types of radios that most people are familiar with, you can start at the very most basic level, and that's a walkie-talkie. Very basic radio, you're talking from one radio to the next and communicating information that way. And believe it or not, across all the different radio technologies, they all work essentially the same. There's some other services that are attached to them, but this walkie-talkie is essentially just the same as this satellite hub station. They both do the same things. They work on the same principles. And so some of the more familiar things that people will know is your cellular networks, your Wi-Fi in your home, Bluetooth things for connecting everything on your desk and your cell phone to your car stereo, things like that. But the takeaway here is that radio is essentially the same across all types of radios, or all wireless. So the principles that hold true for one radio hold true for all radios. Fundamentals of a radio, you're going to take a voice or a data input or information, and you're going to join that with a carrier signal. It's going to get modulated, and all that means is that it gets combined with the two, and the purpose of that is so that you can transmit it at a higher frequency. Those frequencies, they transmit better. We'll talk about that later, over space and through objects. And then you amplify it and you send it out an antenna, and that's the basics of a radio. Now this is very, very basic. If there's an engineer anywhere in the crowd, don't hold me to this. This isn't exactly accurate, but this is the basics of radio communications and how we do things. It can be voice, it can be data, anything that you want to put over that. This is the basics of how that works. Now the radios will vary based on what you need them to do. So a little Bluetooth device on your desk connecting your keyboard to your laptop is going to be a very different radio than a point-to-point microwave meant to connect a cell tower back to a hub location or back to the internet. And so some of the more common radios that people know is a Bluetooth radio. That's a radio that's going to have a antenna about the size of a small postage stamp, very low bandwidth. It's just made to transmit enough information to communicate that this mouse is moving this direction in this way, and it'll negotiate that connection. That's all that it needs to do. Moving all the way up to probably one of the faster signals is in the Wi-Fi area. It's good for about 50 yards. And you can read through this and see, cellular can be anywhere from a block to about 10 miles with speeds up to, at least they're claiming, up to a gig to your phone. And I say that things are a block to a few miles, and that's dependent on frequency and power. And we'll get into that a little later about how all that works. A point-to-point microwave is something that is used to, if you have a remote location and you don't want to, or you can't afford to get fiber out to it or some sort of other cabling, that's when a point-to-point microwave comes in. It can be thought of in a lot of different ways, but a basic point-to-point is used for that, from one location to the next. That's all it's going to do. It's not going anywhere else. Finally is a satellite link, which is obviously from a satellite in orbit to a specific point or a receiver and transmitter on the ground. And that, for some networks, is global coverage. The networks aren't always global coverage. They tend to focus because they don't have endless capacity just on a single area. So there may be a North American satellite, there can be a South American satellite. Regional is how they do it. Right now with Starlink, I've heard and seen things where they're getting 100 megabits on that. And the main takeaway with satellite is a very, very finite resource, and it can be used up rather quickly. So really right now we're in the glory days of Starlink. The possibilities of that getting slower are 100%. And it's an interesting thing that we'll have to keep an eye on. Anybody who's lived in a remote area and had to rely on Hughes or that sort of service can attest to how poorly that can work when that service is used up. You can barely use it during the day, and it works much better at night when nobody is on there. But it's a big step in improvement what they have now with Starlink. For a radio, like I said, the principles are all the same. So how is a radio, what is its perfect world? And that would be a clear line of sight on a cool night. And the couple things here is a clear line of sight. That means that nothing is in the way. And the cool night portion of it is that the air and the atmosphere is another thing that's in the way. So if you are in Florida, when I talk to people that do the same sort of work in Florida, it's a flat area down there and the air is very wet. It's a lot of humidity in it, and it's very hot, and that is a barrier as well. Radio signals don't go through water hardly at all, at least not at the frequencies that we use for radio transmissions. So all these factors, distance, infrastructure, weather, foliage, terrain, and RF, all affect the performance of the radio. So in terms of distance, the distance between one radio and the other is a factor, and you can do a couple things there. You can increase your power, or you can increase the gain on an antenna. And the gain of an antenna is basically how focused that signal is. If you've ever seen a satellite dish or a microwave dish, that parabolic shape is kind of the easiest way to think about that, where you're taking in a greater area and focusing it on one point. That's probably the best example of gain, to where when it receives or transmits, it's doing everything in a very focused fashion. Another example is your car's antenna, and that's an omnidirectional antenna. That is made to gather signals from all directions. No, very, very low gain on there, but it's going to capture signal from any direction. So there's a couple ways to solve your distance factor. As far as infrastructure, this just means buildings in your way. So if you're in the middle of the city, a lot of people would probably have satellite radio. If you drive under a bridge, there's a temporary cutout. If you're in a urban jungle, as it were, say downtown Seattle, driving around with big buildings, you're probably gonna see some cutouts as well. And that just means that you don't have a clear line of sight to the satellite anymore. And that's a function of frequency as well as power, but primarily it's frequency. So your lower frequency signals will propagate better, and you'll be able to receive those more reliably than say a satellite signal, which is at a very high frequency. So a good example of that is your FM radio. You'll almost always be able to receive that within the area of that antenna very reliably. So you can be indoors, outdoors, driving through the city. It takes a lot before you lose a signal like an FM signal, because it's at a lower frequency. And as mentioned before, anything satellite related is very easy to lose, very different frequencies. And those are the results that you get out of it. Weather, like I mentioned before, whenever it's more moisture is held in warm air than in cold air. if you get too cold, it starts to crystallize, and that turns into a lot of reflections, and that becomes a problem. But if it's cool and there's lower humidity in the air, that's kind of ideal. So your weather, if it's raining, snowing, ice especially, it doesn't take very much for that to degrade a signal. Different frequencies are much more resilient than others. If you've ever had a satellite dish, for example, you know that if it's snowing, you're probably going to have to go out and sweep it off to get that to work. Again, FM radio, no problem. You're still getting that signal, and that's based off of the frequency. Foliage kind of comes down to, it's somewhat the shape. So your pine needles versus say a deciduous tree like a maple leaf are different, will have a factor in that, but it kind of comes, the big one is water content as well, and how the how that plant is how much liquid it has in it, the shape of it. Those are the primary things that make foliage a factor. Also, the density of that foliage. If you're going through a few trees is a huge difference than if you're going through a half mile or a quarter mile of trees. And you see radios perform much differently on that. Another good example is satellite. If you have a satellite and you're trying to, you've got your cabin in the woods and you've cut a hole in the trees for your cabin, but you haven't made enough room to get a clear line of sight to a satellite in the sky, it's not going to work. Whereas if you have a local WISP, wireless internet service provider, they may have a service that goes a little bit better because of its frequency and proximity to you that works at all, I guess. It'll operate a lot better. Terrain, this is basically just a hill in your way. Radio will not go through a hill or a mountain for that matter. So a lot of military communications especially is based on getting a voice signal over the next hill over, because everybody that you want to talk to is on the other side of that hill and you can't get a radio signal through there. So that's a primary concern. How it affects people in our realm is finding a nice hilltop location or a higher location, or building a tower that's above whatever is in our way. But primarily we like to use geography to our advantage. The best or the ideal situation is a butte or a hill or a mountain right outside of a city that covers the entire area. So if you drive around, once you start noticing towers, you can't unsee them, and you'll see high locations looking down into lower locations. So any hill, butte, especially in populated areas, these days they're almost everywhere that you'll see. Anything that's a high point will have some sort of a tower on it. It's getting more and more rare these days that they're not there. And finally is RF interference. If you are both on, good example is probably a walkie-talkie. If you're both on that same channel and you're both talking, that's interference. And the principle is essentially the same for any radio. If you have somebody else on your frequency, on your channel, and they're trying to do what you're doing, it interferes and you can't understand it. We can't understand it any better than the machines or the computers will be better at it than we are picking that information out. But the principle is still the same. If somebody's operating on your channel, the process, and it's the same for radios as well, as I didn't understand you, send that again. It doesn't mean that they don't work. If they're both trying to do a lot at the same time, then you'll have that interference, and things will take longer. It's hard to completely, well, it's not hard, but it takes more of a deliberate effort to completely shut down a radio and make it not work, rather than just two sites operating at the same time. And that gets into licensing and specific types of interference. We'll talk about that later. But those are all things that affect a radio signal. And I don't think I addressed the cool night or the night portion of that. In the day, one of the other things that can affect a radio is the principle of ducting. And as ducting happens, that's just the atmosphere separating into different layers. And so you can get essentially a weather channel in different layers of the atmosphere. And this is how you can hear about the old ham operators. You know, a guy in Washington is talking to someone in Greenland via this atmospheric ducting. And there's certain types of radios that operate exclusively on that principle as to how well they function. So that's why I say nighttime, because those type of features are less likely to occur at night. Or if they do occur, you can control that and operate within that. So I kind of went into that lower frequencies propagate better than higher frequencies. Pretty much everybody has a wireless router in their house now, or at least knows somebody that does. And for those that have paid attention to it, the most common bands are your 2.4 gigahertz and your 5 gigahertz. And if you've noticed, you'll get that 2.4 gigahertz signal much better and at a longer range than in your 5 gigahertz, but it will be slower. We used to only have 2.4 gigahertz in the early days of Wi-Fi, and we expanded out to the 5 gigahertz. And the reason that is because a higher frequency is, there's more oscillations per second. Hertz is just a single wavelength. Here in the diagram here, it's a single wavelength. It's a single oscillation of that wavelength. That's 1 hertz over a second. So if you go with 30 kilohertz, that's 30,000 oscillations per second. And then if you get all the way up to 30 gigahertz, that's millions of oscillations per second. And the basics, the easiest way to think about this is the wavelength. If something at a 30 kilohertz wavelength is 10 kilometers long for a single wavelength, whereas 30 gigahertz, a much higher frequency, is 1 centimeter. So the way I've always thought about it is, how hard is it to completely stop that signal? Like that entire oscillation, how easy is that to kill? For lower frequencies or interfere with. For lower frequencies, it's pretty hard, because say you put a wall or a tree mid-span on this oscillation, you haven't necessarily killed the entire thing. You've just, you've made it a little less strong, a little interfered with, but you haven't killed the entire thing. Whereas something that's 1 centimeter in length, you put a tree in there and you've killed a good portion of it. That's kind of probably the easiest way to think about why some signals propagate better, or higher frequency signals propagate better, or I'm sorry, lower frequencies propagate better than higher frequencies. That's the easiest way to do it. In the cellular world, we have the still ongoing, the 4G and the 5G bands. And these are the common bands that they've used. You've got 700, 800, and all the way up to 2300, whereas 5G has multiple bands. There's a low band that's below 1 gig, mid band, and high band. As far as, and what drove this necessity was that lower frequencies, they propagate better, but they don't carry as much information. The modulation that I talked about before, you can only do so many things to this signal to impress data upon it. And once you've maxed that out, you need more of them. And so that's why a higher frequency, you're simply doing more of that modulation on more wavelengths. And so a 1 hertz signal versus a million hertz signal, or a 1 gigahertz signal, is going to have, you're just going to have more chances to read data off it. It's, I guess you could think about it as you flip a single page in the book rather than flipping the entire page, the entire book's worth of pages. You get all that information coming at a different rate. And obviously you don't want to have the best propagation in the world with a very, very low signal, yes, it goes around the earth, but it hardly carries any information. Whereas extremely high signals, they hardly propagate anywhere. Any moisture in the air will knock them down. They're pretty weak. So one of the ideal bands that they have is the mid band, and that's the 1 to 6 gigahertz. That's where everybody likes to be. That's where all the carriers in the cell phone area, as you can see, that's where they've set up shop at. Those are the primary bands. So when you hear about 2.5 gigahertz or the CBRS band or the cell phone bands, that's where all these operate, because they're the ideal combination of frequency and data that they can put on there. It's a good combination of that for humans, I guess, and the way that we typically live our lives in cars, the distance from our cities to the mountains, the type of foliage that we have. It's just a good match for our lifestyle to the amount of information that we need. On the extreme end of that is, I would say, like a submarine. They have extremely low frequencies that propagate very well through water. It's very low bandwidth. You hardly get any information, but that subsea antenna, and these are kilometers in size, they're absolutely enormous, but that signal will propagate clear to the other side of the planet. And so that's a way of tailoring a radio to what you need to do. One of the interesting things in the 5G world, you can see that with the 3 bands here, the low bands, that's primarily still going to be in the areas of 700, 800 megahertz that 4G was using before. And that's for that distance coverage. So when you're driving in your car and you're miles from a tower, that's the band that they're still going to use. Or one of the bands that they can use. Like I said, this mid band still works for that sort of information. But as you go up in frequency, you need to be closer to the tower. So your low band is going to be good for miles, mid band good for miles as well. But once you start getting into these high bands, and that's, I think Verizon's calling it ultra wide, at least according to my monthly bill, they're calling it ultra wide, and it's 24 to 40 gigahertz. And those antennas, you may see them in your neighborhoods if you live in the city, but those are only good for a few blocks, or depending on the density and the type of buildings around there, maybe even a block of coverage. They have, some of them are rolling out broadband to the home via wireless. And if you're in a good enough spot, you can just set it in your window and it'll get inside of the window, and that's fine. It'll give you the speed that you need, but on some others, you'll have to have an externally mounted antenna to connect to that sort of frequency band. But if you want those 1 gig speeds, those ultra fast speeds, you have to be very close to a tower. And again, this is the same for anything. If you go down in the basement of your house and your wireless router is up on the 3rd floor, it's not going to work as well. It's going to be slower. And so you either have to switch to a lower frequency or just accept that your signal is going to be really weak if you stay with the 5 gigahertz. And that, yeah, so high frequency means more towers. So in your neighborhoods, if you see, oh, what do they look like? Just kind of a stick or an extension of the light pole or power pole in your area. That's what that is. That's a 5G ultra wide antenna that they've put on because the range just isn't there. The speed is excellent if you're close to it, but you do have to be close to it. So that's the idea of how a radio works. Like, what is its ideal world? The next is something that we all want, and that is a fast backhaul. What I mean by backhaul is, easiest way to think about it is access to the internet. You are a person with a phone. What's my backhaul? I need to get to the internet. And so backhaul can be applied to anything. It can be say a radio tower, a cell tower. What's its backhaul? Fiber or wireless? What's the backhaul for For your home, well, that's your internet connection. So backhaul is that sort of term. It just means, how am I getting out to the world? For wireless, that's preferably fiber, just because it has the best capacity. That was the previous talk that Chris did, where he addressed that. The capacity for fiber is the greatest. You can do 10 gigs, 100 gigs. We're setting up even a 400 gig link for some of our locations, but the bandwidth, the amount of information that can travel over that is the best. You just have a lot of options, but it's expensive, and sometimes too expensive, or just not possible to get fiber to a location. There may be no fiber within 5-10 miles of it, and what is the terrain over it is just all the Columbia Plateau basalt, a foot below a little bit of soil. So anything that you would do there, even putting in a power pole, is extremely difficult and very costly. And in that case, a good option is to go with a wireless backhaul. And that's using the method that I talked about before, which is a point-to-point microwave. And that sort of radio is still just a basic radio, but it's going to have a large high gain antenna on it. So if you've ever been by a tower and you see the large dishes on there, that's what those do. Those are point-to-point microwaves, and they're simply backhauling from one location to another location to carry data. And they have progressed quite a ways. It used to only be about 45 meg that you could get out of those. And they're depending on the distance, all the factors that I talked about before, depending on the distance and the power that you can pull off, you can get those up to about 2 gig is a pretty average shot out there. The distance on those can go, I think the longest I've ever done is about 60 miles, but more often it's 10, 15, maybe 20 miles on those, and you still get very good speeds. The further apart you get, the lower your speed's going to be, and it gets to kind of not be worth it, depending on what you're trying to accomplish. But that's a radio's perfect world if you can get fast backhaul and a nice clear line of sight. Here is some of the work that we do on a regular basis. This tower down here, that's out on Kamano Island, and it was in need of some sort of a backhaul. And we get asked this question a lot: is here's where our fiber is, here's where this tower is. You have all these landowners in the way. Nothing comes up here along the roads. There's no fiber to this tower, but it needs better communication service. It's slow and it needs a way out. So one of the things that we will do is go find typically another tower. Here is where we found one tower. Here's where we found another tower. And we will assess this path using all of the criteria that I talked about before. How's the line of sight? How's the distance? What sort of radio can we put in there to make that work? So this is an example of that. We find fiber, we find a good backhaul source, and then we say, well, since this guy's isolated, let's do wireless. Or assess wireless and see if we can get out. And this is another tool that we use. There's a bunch of different names for them, but path loss is probably the most common. Link planner is another. But what it does is you say, I've got a tower on this side and a tower on this side, and how is the line of sight through there? So for the first one, the green is good, the red is bad. So when I talk about this on this next slide, that's what we're talking about. This one was closer. So you always hope those will work out. But this is an example. This guy was 5 miles away. That was the green line. It was further away. And you add in the tower heights, and built into these programs is called clutter data. And that is just the trees. These are buildings, these are trees, different foliage, as well as a terrain profile. So anytime you do a radio link, this is one of the very first things that you look at is, can I see it? Is it even possible to do that? And you can see that it was not possible. It hard into the trees as well as into the terrain. So even though it was a shorter path and we would have liked to go there and it had fiber connection, you're just not going to happen on that. So that's for a point-to-point link. Another method that we use is once we do have a tower site, we have a technology that can go and connect to multiple endpoints. The antennas that I talked about before, you have point-to-point antennas that want to connect one point to another point. And those are very focused and they're made to do nothing but connect 2 points. Other type of antennas, and this is like a walkie-talkie type antenna, are called omnidirectional. And that's just a single pole sticking up in the air. It goes in all directions and propagates equally all in those directions. And for that type of connection, we use what's called a heat map. And this heat map is the little triangles here, I'm sorry, the diamond shapes. Those are customers. These are people that we need to reach. Here's the tower, in this case, well pin it. We built a 190-foot tower there and put an let's just say we put an omnidirectional antenna on there. What we actually did is we had a tower and they had sector antennas and they were each good for 65, but you build using pieces an omnidirectional antenna. Those separate antennas, you combine them. So this one does 60 degrees, this one does 60 degrees, and you do a full 360, or you tailor it to the direction that you need. And then the way that you read this is, green is good, red is bad, and varying shades in between. And based on terrain, all the factors that I talked about before, you can see with really good accuracy who you can reach. So in this case, this guy right here, right in the heart of the green, he's not going to have any problems getting that signal. When you start getting into some of the other areas where maybe he's just beyond the backside of the hill, that's something that you would drive and test out, see what kind of signal that they would have. But primarily, once you just, you choose your highest concentration of of customers and you deploy in that location, and you try to cover as many as you can, get the most bang for your buck. And once you do that, then you can run a survey like this and see who's all going to get covered. After that, you kind of have to fill in the blanks. Like you see, there's a good number of people over here that may or not have great coverage. And so that would be where you get, you would put up another location, another tower in that location, or another access point to cover those areas where you don't have coverage, and turn the entire thing green is the ideal. That's an idealized approach. Based on our geography and terrain, you can't ever get everybody, but you can get, depending on how much you want to spend, you can get close.
Sean, I have a couple questions that have come in
Sure.
for you. What tool are you using to create this kind of heat map?
We use a tool that Google provides, but there's a bunch of different versions. If you want to do a Wi-Fi plan, like inside of a building, Ekahau is one example. And then the functionality can be built into any number of programs. But if you just were to Google, heat map creator, that I think, what's a good name of that?
EX.
Yeah.
I'll just mention about what this is right here. So this what we're looking at is we got access to this through Google. Actually, Google created this tool. It's called the Google Network Planner, and we got into this because we started working with what's called CBRS, and I think Sean's going to cover that a little bit. It's a certain band of spectrum you're allowed to use to build these systems that are available to everybody. But to use them, you have to have certified technicians on your staff to operate in that band. And so when NoaNet sent a few people to training to get certified in CBRS, and there's a couple different companies we could go through. We could go through Google, we could go through CommScope, we could go through a Federated Wireless. And NoaNet, we actually sent one person to each to each company that was doing these training, just so we get a good amount of training from everybody that's providing these trainings. So, but what happened is with Google, we sent one person to the Google training, and they provided this tool as part of the training. And so it was a win for us. I mean, it's been a super useful tool to have and have access to it. And actually Google's like developing it at the same time. So we've actually been watching them develop it. Like they've been coming out with different updates for it every few months with it. And, you know, it's interesting because we provide feedback, and they've sort of incorporated that feedback into it. So it's been really useful.
Yeah, there's a lot of commercially available tools. It kind of depends on what you need to do. So the most simple version will be a point-to-point analyzer. One of the things that you pay a lot for is how accurate that data is. So when I was talking about this clutter data, let me see if I go the right way here. Nope. So when I talk about this clutter data, I mean this stuff here, your buildings, your trees. How accurate that is it costs money to get that information. Somebody has to go around and figure that stuff out, either get access to very accurate satellite information or actually go out and do surveys to get that. So that's one of the things that you pay for is accuracy. So for a program like EDX, you can pay big money, like tens of thousands of dollars, to get that really accurate clutter data. And then after that, it comes down to functionality. Are you just doing point-to-point analysis? You won't pay that much for that. A lot of times you can find that stuff even for free. But if you start doing point-to-multipoint and you want to model radios and build in custom antennas, custom frequency plans, custom modulation schemes, or just have them already there and waiting for you, you'll pay big money for that as well. But some common ones are EDX. I just did a quick Google search here for RF survey tools, and it's definitely grown even since I've looked at it. There's some semi-fair ones.
Way for our audience is that you get what you pay for, and there's a lot of resources out there if they want to.
Yeah.
I just want to be time. We have a couple really great questions in here, but I'm aware that it is 12:43. So, and I know you have a great information.
Wow. Yeah. I'm sorry. Really. Yeah. Well, you have to talk to an engineer. This is what we do. We will deep dive if you give us the chance. So let me move on.
Live, I will email you, and we'll follow up.
Sure. Yeah. Okay. Well, I need to hurry then. I didn't think I'd talk this long. So the next biggie is once you know that you have a good location and it has a clear line of sight to either your customers or where you want to go, then you actually need to get the spectrum, which is the radio frequency section that you want to use. Like I said, there's all kinds of different radios. There's Bluetooth, there's Wi-Fi, there's point-to-point microwave. All that stuff uses different frequencies so that the radio acts how you want. The ringleader of all that is the FCC, and they control every sort of spectrum that we have available for radios. That spectrum is extremely valuable. Hundreds of billions of dollars is not at all an exaggeration. They just sold off they do auctions, and they just sold off, slivers of network. And providers like Verizon, AT&T pay, I think the last one for, I think it was 100 megahertz of spectrum was $9 billion. So it is big, big money. FCC prioritizes military and first responders and designated groups that they select. They leave things open for the public in some areas, but those are kind of the three tiers: is people who have priority, that you would want to have priority, the military and your first responders, and then people that have paid for it to use that spectrum, and then everybody else is kind of how they do things. And that leads to licensed, unlicensed, and lightly licensed. Licensed it's exactly what it sounds like. You go out and you buy the license to use that spectrum. The takeaway from that is that it is controlled and monitored. And if you've paid $9 billion for spectrum, you absolutely hunt down anybody who is using your spectrum or channels. That is something that they definitely will do. So when you hear about people, oh, I'm on this radio channel and hope nobody catches me, it probably means they don't really care. You get your guys buying radios off Amazon and broadcasting on top of people. Nobody really cares. But if you come up on KEXP's channel and you start interfering with their TV broadcasts, yeah, you can bet that within the hour somebody will be coming and looking at what's going on there. Unlicensed, a good example is Wi-Fi. That's in your house. Everybody has it. And I included this picture right here because this is what any unlicensed spectrum eventually turns into. Everybody's on it. Everybody's using it. It's an absolute nightmare. Like I said, radios don't just stop working, but they have to retransmit. So this is, your average densely packed apartment building, and everybody's got a Wi-Fi router. And this is what that spectrum would look like. And it's not going to work well. And, it'll work, just not well. But this is what pretty much anything unlicensed turns into. Lightly licensed, which isn't, I don't think, an official term. I didn't see the FCC refer to it in any way, but it's the way of, on some of the spectrum that they're freeing up now, they've made it very easy to get in there. You basically go in and ask, and if it's available, it's all automated, and they say, yep, you're good to go. We know what's out there. Use it. That's lightly licensed. Moving on, this is what I was talking about. This is all the spectrum in the United States. Each country, so Europe would have their own, Asia would have their own, country will do their own. And when I talk about spectrum, this is everything. This is what I'm talking about. This is the orange area right here. This is the entire radio spectrum. Once you get up here, again, this is all just frequencies. So infrared, this is your visible light, get up to X-rays and gamma and cosmic rays. But we're talking about this little section right in here. And you can see how broken up it is. The section that we're going to talk about is 3.5 gigahertz, or the CBRS area. And that is just this little section right in here. And you kind of have to zoom into it and look at it. And then that is it right there. And you can see how it was broken up. And I almost guarantee you that this is not correct. Like this picture has been out forever, and things have changed a lot since then. So you really can't reference just this because it changes all the time. But this is a good reference for how kind of crazy spectrum management is. It's an ongoing and constant thing. Depending on the band, it is very closely watched. But they're trying to, where they can, they optimize use. And that, especially CBRS is a good example of that, where they had a band that wasn't being used too much, except by a very specific group. So they opened it up to be better utilized because, as you can see, spectrum is very hard to get and very valuable. So move on here. Why choose wireless broadband? Kind of goes to the things that we talked about. You can cover a large area with a single site. Once you get on that hillside and set a tower up, you can cover huge swaths of land. And all you have to do is set up the customer end, which is usually some relatively cheap and simple equipment, and off you go. That's all that you need. I say usually cheaper. It's almost always cheaper to set that up unless you're in the city. Within cities, it's not that great of an option if you're trying to get to customers' homes. It can be not that great of an option, but if you're looking for diversity in supplier, then it's a great option. If you're looking to not be a multi-billion-dollar corporation and get options to customers, it's an excellent option because you can cover a large area. And it's going to work out. If you're competing with somebody that has something directly to their home, it may not be as fast. You may not be as competitive in that area. But if they don't need something that is in the gigabit speed range and they want options, this is a great way to do it. Faster deployment, there are fiber supply issues right now. From what I've heard, a lot of fiber projects have a 1 to 4 year timeline depending on what they're trying to accomplish. So in the meantime, wireless is a great way to go. Lower cost and a lot of return on investment. The other thing
I'm gonna give a 10-minute warning here.
Okay. Don't need dedicated towers. Water towers and buildings work just as well. And again, customer equipment is relatively minimal. So let's get into, this is something that Chris had alluded to in his talk about broadband. The 3 basic types, your fixed, your mobile, and your satellite. Your fixed wireless is coming from, it just means that neither of the points are moving. So from your WISP, your wireless internet service provider, to your house, nothing moves there. The point-to-point links that I talked about, they don't move as well. Mobile wireless, that's cellular, that's driving in your car and talking to a tower. One of the things about that is it's the most common and has the most customers probably, and so it gets the most upgrades. They're always trying to make it faster and better. It gets the most attention. Satellite, honestly, there's only one worth talking about in my opinion that can, actually do what is termed by the FCC as broadband 25.3, and that's Starlink. It's working great now, but again, we'll look at it once there's millions of people on it. Here is a fixed wireless CPE. This is the customer end equipment. That's why I say it's pretty easy to get onto that stuff. You just need this and a power supply, and you're off and running. This is a monopole tower, multi-use. You can hang pretty much anything that you want on there. Here's a water tower example and the satellite dish. So these are kind of the primary broadband methods that you'll see around town. I didn't include a building, mostly because I couldn't find a great picture. What people like to do is take those antennas and then put clever designs on them so they kind of sink back into the building. I don't know if it'd be visible on the picture, but tons of stuff hanging from buildings out there once you start looking for it. Here is some of NoaNet specific equipment. This CPE that you saw right there you can see the form factor on that, or the size. This is what we use, at least right now, is a Telrad version of that. They're all basically the same, but this is it. When I say a simple installation, this is basically it. Here's one of our towers that we have, and here from the top of it is the wireless broadband equipment that we've deployed. Down bottom, you've got a power supply. Here's your radio, and here's your antenna. This type of antenna is called a sector antenna, and it covers about a 60-degree swath of land out in front of it, rather than your point-to-points, which are just point-to-point. This is a point-to-multi-point, and it covers a 60-degree swath of land out to about 5 or 7 miles, depending on what's in its way. But this is actual NoaNet equipment or NoaNet deployments. Here is a fixed wireless scenario where you have a tower or a location, doesn't have to be a tower, it could be anything, and it has a fiber connection back to the world or out to the internet, and you would hang your point-to-multipoint system off of that. That was the example that I just showed you, where you get a sector antenna and it'll come out to, or an omnidirectional antenna, out to these houses, and you get that connection and it's immediately back to the fiber. This is ideal, but it doesn't always happen. What you usually have to go with is this antenna or this tower is out in the middle of nowhere. It's going to cost hundreds and hundreds of thousands of dollars to get fiber out there and power and everything else. So what we'll do is we'll go to another location, and since your mobile wireless or your cellular towers are the most common out there, we'll put a point-to-point microwave system to connect back over there, giving us a few gigabits of backhaul, and then we can do our fixed wireless deployment. And these are the two primary methods that people use to get fixed wireless out there, or broadband wireless deployed. Primary one that we've used in the past, the 2.5 gigahertz service. and it's all licensed. It was sold at auction. T-Mobile is kind of the primary on there. They're wanting to have another auction for that space. There was a tribal priority given to the tribes throughout the country, and that is something that we've taken advantage of on the Colville and the Spokane tribe areas. We have deployments active for using this spectrum, and it has been really very, very good for us. The 2.5 gigahertz is one of those excellent pieces of spectrum. They perform very well. They go through trees well. You get good speed out of it. And this is what we've gotten on some of our smaller 20 megahertz channels. We've been able to do 110 down, 12 meg up, and then you can combine those two and get 220 down and 24 up, or roughly around those numbers on a perfect shot. But those are we've been very impressed with that spectrum and that equipment, and these are some of the things that we're seeing out of those. Next one is the CBRS. This was old military band used on the coast and some fixed satellite, but they freed that up because it wasn't being used hardly anywhere. So they freed it up, and each county has available 7 10 megahertz blocks, and it's lightly licensed. The only people that you have to yield to are the incumbents, which is the military users or the government users that had it. Anybody that bought an official license for it, there was also 70 megahertz sold off as priority. Those are license holders, so anything you deploy will give way to them. And then what is available is the general authorized access, and that's the lightly licensed portion. That's what Greg was talking about, where you have a certified installer, and you go to the SAS website, the Spectrum Access System, and it's basically a website, pulls up a map. It's probably easiest just to show you here. This is what Google has. This is the SAS system. And here is, you can see a whole lot of green here, and that's good. But what you would do is you would go in and you would say, I want to set up shop right here in Kennewick, and what's available to me. Oh, wrong way. And zoom in there and you can see, oh, there's plenty here. And these are and it's really just point and click and make your reservation if it's available. You would come in here and select the bandwidth that you want, the direction that you're going to go, your location, and it's telling you, it will tell you because it's constantly monitored. Built into all this equipment is survey tools that monitor the spectrum and say whether or not it's available. And it's that easy. This is the licensing portion of it. Is you go in, you ask for it. If you're good, then that's it. You can use that spectrum, and it constantly monitors and returns unused spectrum for use. So it's very, very efficient. And this is one of the areas that we're most excited about. This is a great way to deploy wireless broadband for a pretty low cost in comparison to other things. So that's it. NoaNet really focuses on getting service to areas that doesn't have it, the underserved. And these tools that I talk about, sorry things were so lopsided on the theory side, lost track of time here. But those are the primary tools that are available right now, and technologies and hardware. The method won't change, the architecture won't change too much. The equipment will change over time like it always does, but that's primarily how you would deploy wireless broadband out there.
Sean, that was fantastic. And I really appreciated actually all the theory, because it was like you taught us to fish. I really feel like I could more intuitively understand some of these technologies now that I understand more of how it's working. So that was fantastic. And
yeah, it's important to set expectations of the technology. A lot of people think, you can just hang it on a tower, you get infinite range and infinite performance. So rather than set yourself up for disappointment, it's important to know the challenges that are involved, how much work goes into it. It's a great method for getting stuff out there compared to running a fiber or a cable to each person's house. But as long as you know the limitations of it and how to set it up, you really constrain your expectations. And within that envelope, it's an excellent option.
Well, thank you both so much, Greg and Sean, for your time and for sharing your expertise with us on this very complicated topic. You just scrolled to see the emails right there. So go ahead and reach out to these guys if you have any more questions that we weren't able to get to today. And I'm going to post this video and this slide deck on our website under community resources, the video resource library. So you're welcome to review later at your leisure. So thanks so much, everyone, for joining us. And we wish you a wonderful afternoon.
Thank you, everybody. Bye-bye.